Want to do more with your 3D printer? The L-Cheapo Mk5 is a laser that can be mounted on 3D printers and CNC mills to allow engraving and cutting of most materials. 8 watts continuous output let you cut acrylic and wood, engrave on metal, and make printed circuit boards. Made in the USA, runs on 12-volt, 24-volt, or a laptop power brick. Buy it now or make it yourself. Open source design.
Alright, that was the sales pitch. However, I am not here to sell you my laser. I appreciate it if you buy it, but I am going to show you how to build them. All my designs are released under a Creative Commons license attribution non-commercial share-alike, meaning you have my permission, my blessing, and my encouragement to copy the design, to riff on it, and pretty much do whatever you want with it. The only thing I ask is that if you adapt the design, the adaptation must be released for free, and that you do not sell copies of my designs or adaptations thereof for profit. In other words, don't become my competitor. Otherwise, I will not be able to pay bills and I will have to stop releasing stuff for free. Well, that's the legalese, so let's get on with it and on with the build.
Today I'm going to show you how to build the L-Cheapo Mk5 solid-state laser cutter. Normally I don't cut my videos, I try to do everything in one take because I want people to see that what you see is what you get. However, this is going to take some amount of time. It will take about an hour for me to do. So I will be cutting off some pieces because you will get the idea. I will do this as little as possible, but this will be a departure from my usual performance, quote unquote. So this is the PCB. You can download this from my wiki. Note that some of the resistors are actually etched in as traces. The most important thing you should notice is that one side will have letters. That's the front. It used to be that these resistors were something you had to solder on. You had to solder in 16 5.6 ohm resistors. So I still got a bunch left. But I found that Sunstone and 4PCB will make these traces with enough accuracy to substitute for those resistors. So let's look at the parts. You're going to need, first thing you're going to need is some kind of a beefy diode. Anything will do, really, as long as it's, the voltage drop is not too short. This guy is an NF-J62 6G. Again, there's a parts list on the wiki. You can just use that. And this guy goes in here. Next, you're going to need a Mosfet. And any beefy N-channel Mosfet will do. The IRF Z series will do fine. Lately, I have been using IRL640A because I happen to like them. Note that the board has holes for two transistors. That's in case you have, that's in case you can only get smaller MOSFETs you can put into in parallel. Now, one thing that's very important when you solder this in is that these two parts must not touch. Next up is the optional tilt switch. Now, what this little guy does, see if you can hear it. What this little guy does is that it makes sure that the laser will only fire when aimed downwards. It's kind of important. It's optional, you can go without if you like, but I think it's a good idea to have it. This guy will go in here. Next, most important, this is really what makes the whole damn thing work, is we have two LM338 regulators. Now these are going to go in a bit funny because they're going to have to, one of them is going to go in front and that's going to carry most of the current, which is why the fan also removes heat from it, and the other one is going to go in the back. Now before you put it in, you're going to have to cut the legs of the one in front. Again, I'm just fishing out the parts right now. So make sure we get everything where it belongs. Okay, that's all we need. That's pretty much it for active components. Now we're going to need some resistors. We're going to need a 4.7 ohm resistor for the PWM input. Yeah, it's not even that many parts if you look at it. We're going to need a 4.7K for the PWM input. We're going to need a 47K to 100K for grounding the gate on the Mosfet, because we don't want this thing to turn on by itself. And then we're going to need something that plays nice with the opto-isolator that we use as a tilt switch. This is a 390 ohm. And this is all the standard components you need. Next up, we're going to need a fan. Here's the fan. You can get a few types of 5-volt fans. We're actually going to drive them at about 8.2 volts. They can take it, don't worry. These are fairly good. They're kind of loud, which I think is a good thing because you want to know when the laser is on. This is a Pwm 5010. Lots of airflow. Very good for that. Next we're going to need, sorry for the mess here, but that's where I work, so. This is the evolutionary improvement of the LM2596 voltage regulator. You can buy these off Amazon. It's called the XL4005. Note that I have removed the chip on it. That's because we're going to put in 2 different chips. They are also going to be 4L05s. However, for this build, it's very important that they come from the same factory and they come from the same batch, because this thing will be a lot happier from a heat point of view if they match closely. So we're going to need 2 of these. And this is all we need for the circuit part. Afterwards, we're going to have to put together the actual laser part. Now you can only see my little lamp here, so I'm going to pause the video and move this so you can see me work. So the first thing we're doing is we're making the board. This is the L-Cheapo board. You can download the Gerber files from my wiki. There's also an older version. Now note here that the resistors, so you used to have to solder on a bunch of resistors, a bunch of 5.6 ohm resistors. I got a bunch left here. But the new version has them etched into the PCB. I found that 4PCB.com and Sunstone.com are consistent and repeatable enough that I can trust them to give me the same amount of resistance. So this is tin plated, and the thickness of the copper plating is 1 ounce, which is their standard hobby grade offering. So that said, you won't have to solder in a bunch of resistors here anymore. Now the operating principle for this thing is very simple. You have a voltage regulator that goes in the back. Bring down the voltage from either 12 or 24 volts or anything in between to approximately 8.25 volts. And then you have, that runs the fan. and then you have two current sources running in parallel, providing power to the diode. Now the trick here is that these current sources thermoregulate by being exposed to the heat generated by the diode and lowering their output accordingly. This gives you just a little bit of negative feedback to make sure that you don't blow the laser up. So the first thing we're going to need two LM338s. We're going to need a beefy N-channel Mosfet. Now this guy is an IRL 640A. If you cannot find, this guy is rated at about, I think it's about 120 amps peak and 60 continuous, which is absolute overkill, but you know, can't hurt. Now if you cannot find a big Mosfet, you can use two small ones, again in parallel. There are two sets of holes here. We're going to need a diode for this guy, and what I've been using is I use the NFJ26G. Again, pure overkill. This handles about 40 amps. But you know, it's a nice form factor. You can also use something shaped like this. Now this is what I use for the Mark IV. This is a 1N series that's rated 5 amps. And this is why, by the way, the holes for the diode are thicker. That allows you to put in both diode types. We're building a Mark V today, so we're going to use the big diode. We're going to need 3 resistors. One is going to be 390, 330 to 470 ohm for the tilt switch. Speaking of which, tilt switch up here. Now this one, I don't actually have the part number. It's not written down here, but it is written on my website. You can get these with a 15-degree tilt angle or a 45. This guy is a 15, as you can hopefully see. It's basically what's in here is that it's a phototransistor. It's an LED. There's a little ball. You can hear it. And there's a little cup that the bulb falls into, and that's your tilt switch. What it does is that it makes sure that the laser only fires if it's aimed downwards. Then we need a 4.7K ohm resistor right up here. And then we need something to pull down the gate on the Mosfet. That can be pretty much anything. It could be a 47K, it could be a 56K, 100K. Whatever you have around in that range. I'm just going to use a 47K because I have a bunch of them. There we go. And these are all the parts you need. Of course, you're also going to need a fan. I already pointed out which one it is. Here it is. This is a Kui 5010. It's rated at 5 volts. It runs just fine at 9. I'm going to run it at 8 1/4. So it will run, it will be very loud, but they last year, so I'm not worried about it. The thing you're going to have to do is we're going to have to trim this a bit. And so these are all the parts that we need, and I'm going to interrupt the video because if it gets too long, the camera acts up. And you're going to see me build the thing right in front of you. Afterwards, we're going to have to modify the 4005 so that it can handle more current, and afterwards we're going to do the metal work necessary to put the diode inside the heatsink in a way that will secure correct heat transfer both away from the diode and from the diode to the board. Note that there's a lot. Note that this is not connected here. The future revisions are going to have a jagged edge to improve thermal conductivity, actually. So let me. Oh, you will not. You can just use solder. You don't need thermal paste for this part. You will need thermal paste later, though. So this is a simple build with reasonably small amount of parts, and let's dive right into it after the break. This circuit is simple. It can be built using only through-hole soldering skills. You will need, though, you're going to need a reasonably small soldering iron, and you will need a larger one because there are a few spots here and later that you need to put a large amount of solder down, and it has to all be at the same temperature. So let's actually start with that. This is an LM338. So the front, by the way, the front of the board is the one that has some lettering on it. So, front of the board, the first LM338 goes into the lower set of holes, right like so. And we're going to do the legs, and then we're going to have to make very sure that, one, the flange is very well connected electrically and thermally to this land, and it does not touch the land on the back, because the two flanges on the 2338s cannot touch each other. Otherwise, they will connect. Basically, you can't connect two LM338s in parallel if you use them as current sources, if you're careful. If the flanges touch, though, what's going to happen is that one of them is going to carry most of the current, and you lose the benefit. Plus, the way that this is set up, one of the front LM338 is carrying most of the current, but in a controlled manner. It's about a 70-30 split. That's because the front one is also getting active cooling. The one in the back is just getting passive cooling. So on the back, we're going to have to get the other LM338. And this one, you gotta be careful here, because if you just put it in here and then just bend it, it might touch its little sister there, and we don't like that. So instead, we're gonna have to bend the pins ourselves. Now again, this is a simple circuit. It does not lend itself to be built automatically, because there's components on both sides, because you have to do all sort of little things. There we go, that's better. Nice, should be a bit more than a right angle. Again, these two components can see each other thermally, but at least as far as the center terminals are concerned, not electrically. That's important. So after I solder the legs, we're going to have to solder in the flanges, and that will have to be done with some care. Now the board, I try to design it in such a way that vias are not too close to each other, and most through-hole pins have little lands to the side that you can kind of shunt any extra solder on to make it easy to build. This board was designed to be buildable by a 12-year-old on the first try, which fortunately enough has happened. It was a fairly nice science project for one of my neighbor's kids. So this is what it should look like. Now we're going to do the flanges. This is where you break out the big soldering iron. You make very sure that these two are not touching. There has to be some board here. This board here can be as thin as you like. The thinner the better, because again, parts have to see each other thermally. Of course, if you make it too thin, it might break. I find that 037 works as for sandstone. 4PCB offers more options. The smallest I've had it made was 4 mils, and it worked. It worked well. I don't know if I would trust that with shipping. So let's see what we did here. We got a solder down the flanges. We got to push down a bit. I'm going to use this pair of dikes to push the component down so that it properly connects to the land. And one thing that's important is that solder should not go past the land and into these other two lands. If it does on one side, it's okay, but if it does on both, it means that the two flanges are connected, which you don't want. This also makes sure that the heatsink does not have a net associated with, because again, on the LM334, if you connect it to the current source, the flange is not ground. It's not ground. It's at a voltage, and you don't want it to touch ground generally. So let's do that again. Now this is really the only tough bit of soldering that exists in this design. You're going to have to basically use the same trick as you will see later on the voltage regulator. So this is what it looks like. Again, don't forget, this is the front. You can tell which one is the front because it has little letters etched to hand. So for example, this one said front line, back line. Alright, next up we have the MOSFET. This is just, regular issue N-channel MOSFET. Now this one can go in either in the front like so, or in the back, and if you connect it to the back, you're gonna have to bend it down. If you put it in front, remember the fan will either be up here with the aluminum housing or down here with the plastic housing. So that means that the MOSFET will get some cooling. It's not strictly necessary because again, this MOSFET is way over dimensioned even without any heatsink. In operation, it does get a little warm, but you can touch it. You can feel that it's warm, but you can definitely touch it. Again, from now on, this is just pure standard issue true hole soldering, really. Don't have to do anything crazy to it. Okay, now the diode. So the cathode on the diode goes on the side of where we're gonna put the negative terminal for the whole design, obviously. The purpose of existence of this diode is just to make sure that if you happen to connect this build upside down, so you connect positive to black and negative to red, nothing bad happens. This is done because this laser was designed to go on the extruder heater terminals on a 3D printer. So sometimes the polarity of those are not marked, so I wanted to make sure that customers could just trial and error. Another thing, when you put this in, make very sure that the two flanges do not touch. They have to be separated a bit. Best way to do it is just hold up, just put the board down like this, let the MOSFET hold it up, and just solder it like this so that they are nice and parallel. Plus it looks a bit nicer. Nothing fancy here. This is all the components are pretty spread out. For the resistors, you can use either true hole or surface mount because there's a little land that you can use for surface mount stuff. You can kind of see it here. I prefer to use true hole because, again, I want this to be easy to make. So, first resistor going in is the 4.7. Okay, now this one goes from the input on the Pwm input to the gate on the MOSFET, and it's mostly there to make sure that whatever happens, whatever the input is connected to, doesn't get any nasty backlash of 12 or 24 volts at a high current in case something borks. The other reason why it's there is that the tilt switch works as a pull down, so it must be able to defeat, quote unquote, the resistor. if it needs to. Now, one thing you're going to have to do is you're going to have to keep the resistor legs because we're going to reuse those. There we go, nice and simple. Again, keep the legs. We're gonna reuse 4 legs, and we end up 6 because we got 3 resistors. It's not too bad. Next resistor going in is gonna be the 47K. Now this one simply pulls down the gate to ground. Pulls down the gate. Now you can, by the way, resistors too, you can either put them up here or you can put them in the back. And I'm just gonna put the others in the back because they're easier to see that way. So there we go. Again, all this one does is that it pulls down the gate on the Mosfet. Reason being is that otherwise the PWM wire acts as an antenna, and we don't want any accidental turning on. There we go. That's a bit too much solder if you ask me. Let's get rid of some. Not the happiest little accident. Bob Ross, I am not. But again, keep the legs. We're going to need the legs in a bit. Finally, the third resistor is a 330 to 470 ohm that is used to power the LED for the tilt switch. And this one goes here. Note that you have a somewhat sizable 100 mil prototyping area in this design. I encourage you to make use of it if you can. No idea for what, but you can. Unfortunately, the tilt switch eats into some of it a little bit. There we go. And again, keep the legs. We should have 4 legs out of the 6 we have. Now the next part is really the only part here that, other than the 338, that is not able to go on either side. This one has to go in the back. The other job that it has is that it makes sure that your blue board does not touch the yellow board. So it goes in like this. Note the pins. It goes into the pins that have stuff going to them, and you just solder it in. You just solder them in. That's all you gotta do. Be very sure that the LED is on the bottom and the phototransistor is on top. Since the fan goes here, now you gotta trim the legs for the tilt switch very well. By the way, these tilt switches work surprisingly well as if you want to use them as opto-isolators. I found you just put them horizontal, and that's basically the board. Now we gotta add the fan and the wires for powering it and giving it a PWM signal. Now if you're not using PWM, you can just short the PWM to the positive terminal or to the plus out terminal on the blue board, and you're good to go. So here's the fan terminal. There's you can see there's 5. Now these bottom 2 are the negative. These top 2 are the positive, and this one next to it is a positive that uses plus input V instead of the 8.25 volts that we're going to give to this fan. You know, in case you want to have a 12-volt fan or a 24-volt fan. I've never seen the need for it personally, but it's there if you need it. There's also 2 sets of holes specifically so that you can have 2 fans. I will sell it to you with 1 fan. 1 fan is sufficient for most setups, but I wanted people to be able to have a bit more airflow if they so choose. Again, nothing fancy here, just through hole soldering. Voila. So that's the board. Now, you're going to need some kind of power cable for it. The current requirement is actually fairly high, so you want to use decent wire. Assume that you're going to be sending 5 amps through the power inputs. Now, this is not the case. It's over-dimensioned, but as I'm sure you know, this is exactly the kind of thing that you want to over-dimension. By the way, I'm looking forward to the YouTube comments telling me how messy my workspace is. You know what? I don't care. I am reasonably happy with my workspace as it is. I do have to clean up, but that's outside of the scope of this video, and besides, I think that this kind of video tends to be over-curated usually anyway. So, now one thing you could do, note that this is very thin. This is as thin as I could get. I think it's 28 AWG. I installed this particular wire to remind the customers that there is almost no current going through the PWM wire. There's a couple of milliamps. It just has to, defeat the pull down that we just installed. You can also use a standard issue 3-wire servo cable if you like. I just wanted to make sure that I just wanted to make it very obvious that that's a signal wire. Now there are 2 holes here. You can see them, 1 and 2. So the one that's closest to where it says plus here is where the positive terminal goes. I'll admit this is a bit of a pain in the neck to get to. The negative, is also a pain in the neck to get to. It's right here. It's right under the cathode of the diode, which is where it's connected to. The big hole here is the via by the plating for it is also connected to negative. If you want to use that as a ground, you can. It's just so that you can pass these wires through it for a bit of mechanical relief. There we go. Maybe we can. There we go. A little extra light, maybe. The problem is that if I have the flash on, this is all shiny, and if I don't, you can't really see. So here it is, very simple. Last one is this guy. Again, very thin. If you don't want to use it, you just short it to the red, which is easy to do. So remember that hole that we didn't use earlier, that's next to the resistor. That's exactly where we're going. There we go. Okay, clean up any protrusions if you can, of course. And this is the end of the board. Next, I'm going to have to show you how to build this guy. For now, this is done. And to indicate the fact that it's done, we're going to pass this through here. Just thread the needle. And then in the space that's left, we're going to pass the PWM wire. And that's your board. That's our yellow board. Now, what did we keep the resistor legs for? We're going to use them to connect the blue board to the yellow board. And it's going to go like this. They're going to stick out like this. That's after the break. And we're back. So in the earlier video we've built this board here. Let me remind you the features. So this is an LM338 with the flange very securely soldered to the land here. Same thing on the other side. Note that these two are not connected together. These are the pins for the one in the back. This is the fan connector. This is gonna be, by the way, this is gonna be red, black, black, red. This is where the laser will go. Mosfet, diode, tilt switch, and power and the PWM line using the strain hole here, and resistors. 4.7K, 390, 47 to 100K. Okay, so next up we're going to have to build our high capacity 4005. Now, ordinarily you never put two voltage sources in parallel, but in this case we only need a little bit more current that one of these guys can provide. So after checking it over, I found that it's safe to do so. So the first thing you want to do is you want to remove the original chip. I find that the fastest way to do it is apply heat to this land, pry it up, and then just cut these. So next up we're gonna remove what's left of the pins, if there are any. I don't really need them. Again, the reason why you're doing this is that if you're putting two chips on this guy, you want to make sure that they came from the same factory and from the same batch. So what you do is you order a bunch of them and you just, put them in there. With the leftovers, you know that those are going to be from the same batch if you order it from the same place. If you order these in bulk from the H-gate, for example. So you can probably just prepare another batch with those. As long as you're consistent, you're good. So make sure that this is nice and flat. And then we're going to have to solder the first one of these in there. Nothing strange, nothing too strange about it. I like to shorten the legs a little bit to give myself a bit more room on the pads, but that is a matter of personal preference, really. Let's see, let's zoom in a bit. There we you just, solder it in. Nothing fancy. Again, you may have noticed that none of this requires more skill than just a bit of careful through hole soldering. Not even that careful, because the closest places you'll have to solder are, maybe 10, maybe 8 mils. So this is doable. You don't have to be crazy good at soldering to do this. Now, one thing that's important to note is that the two rightmost pins are actually connected on the board, so if you happen to connect them like this, it doesn't hurt anything. In fact, it helps with the heat transfer, so please do. Yeah, it's not mandatory, but it helps. Let's get the other 3 pins in the usual way. Okay. Now the tricky part. You got your second chip. You gotta bend the legs like so. So that the chip is kind of sitting. You cut a little bit of the legs because you don't want them sticking out. Give it a nice trim. There we go. And then you gotta stand it on top of the other chip. Now they should tessellate. They should, match. And of course they should match pin by pin. Now the soldering here is gonna be somewhat annoying. Like I said, one bit of tricky soldering is putting a lot of solder on the LM338s. The other tricky bit of soldering is this. Fortunately, it's the last one you have to do. So all you gotta do is just solder these in pin to pin. Just connect everything in parallel, which again is not really the best idea for voltage sources, but we have tested these things and we know that they can take. Again, since the rightmost pins go together, you can kind of, be imprecise here and put a bit of extra solder here to just kind of sort of anchor it to make it easier on yourself. And then all you have to do, now this is the part where you have to be careful though, because if you mess up this part in a way that some of the connectors don't touch, the laser will still look like it works, it will just fail after a few minutes due to overheating. There we go. Now you can see that I flubbed it here. I have connected the two leftmost pins together. That's a bad thing. Don't do that. So I'm going to have to take a solder sucker to it. Now one thing is, on these connectors, be generous, because you also want to transfer heat between these two chips as much as possible. So be a bit generous, be okay with a bit of solder blob. Thermal conductivity is important. This is a good result. Next up, bit of thermal paste on this surface. Finally, you take the little heat sink that you should have gotten with the 4005 and put it in this position. And you angle it so that the top chip is pushing down on the bottom chip a bit. There we go. So this is the result. By the way, this is actually a generic trick. If this guy is rated for 5 amps, this will not give you 10 amps, but if you need 6 or 7, I found that you're good to go like this. So that's the other part. Let me take a quick break before I put the two together. And we're back. Okay, so we got blue board, yellow board. We gotta put them together. Now remember those resistor legs that I told you to save? Here's where they go. It sounds like I'm cooking. Jesus. Well, you know, between cooking and electronics, there are enough similarities that I should not be ashamed of it. So you see these big 4 holes. Let me show them to you on an empty board. 1, 2, 3, and 4. Note that this one isn't connected to anything, it's just mechanical, that's just the other ground connection. That's where the blue board goes. Now, before you do any of this, though, you want to make sure that the output on this guy is about 825 volts. Now, even if you set it before, you've changed the chip, so that will change. Now, I've built a little rig to do them quickly. You don't have to. You can just use like a regular, regular voltmeter. I just made myself this little thing so that I can quickly tell what's going on with it. So in this case, it's a bit high. Now, one thing that's important, it has to have a load. Okay. You must put some load through it. I got about 2 amps going through this guy. That's important because otherwise you will not get a true reading. So I want to bring it down a bit. 825, that's good enough. Okay, now you can actually solder this guy in. Now this is not going to damage the diode if you don't remember to do it, but it will blow up the fan. So what you want to do is you want to get those 4 holes filled in with the legs of the resistors that you just cut. You can use another piece of wire. Surprisingly, 1/8 watt for this is good enough for the current. They will get a little hot. That is not a bad thing in this design. So that's one. That's 2. That's 3. And that's 4. They should stick out to the back of the board. All you gotta do next is just put the board in the right place. By the way, note that the chip goes downwards, and the pot goes upwards. Now, why are we doing this? Because 1, we want some air to pass between the 2 boards, and 2, I found that the dimensions of your LM2596 or XL4005, depending on where you buy it, are different. So, they might be this long, they might be this long, it's a bit annoying. So this makes sure that these guys can bend enough to cover any difference. So you just gotta solder them in place. That's literally all you have to do. And there we go. There it is. You just gotta cut off the legs. Happily enough, the tilt switch acts as a spacer. If you did not put in the tilt switch, there is a spacer in the 3D printed shroud. Okay, so that's basically all you have to do for the board. This is what it should look like. And now we can do the metal work, because we gotta take a heatsink, make some holes in it, and carefully stick a diode through it. So let's take a break, and we'll do that after the break. Okay, we're back. So what you gotta do next is we gotta make a hole in this heatsink so that they will fit the laser. Now this is the part where you need to put a bit of precision to it, because it has to be perfectly vertical. Now this is the laser holder, and what you see here, this is a drill. This is one of those things you can buy at a hardware store to make sure your holes are vertical. And the blue part you see in here is a jig that I 3D printed. You can get the schematic. There's a there's one. There's a fresh one. They eventually do crap out because, you know, plastic versus metal, we know who wins. And here's an offset one. The offset one is going to be used later. I don't know if you can see it. There he goes. Let me trace. There we go. That's better. For now, we have the centered one in there. Now, I don't want to make a mess, so I'm going to put my shop vac to use here. So I will not be doing much talking for this part of the video. Sorry in advance for the noise. We have a hole. That's nice. Now, as a quick reminder, the size of this drill bit is 29/64 of an inch. And yes, it has to be that. Don't buy a metric, it has to be that. This is your 9mm laser holder slug, and this is the part where it does not fit. Why? Because we're press fitting it. So you're gonna need a spacer. You can use a key ring. You can use a spacer from a hard drive. You know, whichever feels better for you. I prefer these because it's more precise, obviously. You know, busted hard drive, you just fish one out. But again, you can use a key ring. You don't have to make it complicated. And then we're going to need a vise. It has to be a beefy vise because we have to use it as a press. Surprisingly, this does not damage the vise. Now, one thing you notice is that, see this part here? On this side, I have turned it around because we want this part to be flat. This part is normal. And when you're done making the laser, you can just flip it back. Now this is the part where you gotta put a bit of strength in it. Actually, you know what? Let's use the key ring just to show you that you don't have to sacrifice a dead drive for this. go. And this is the part where, again, you put a bit of strength into it. You should go clunk. That was clunk. Give it a good squeeze. When you're done giving it a squeeze, you flip it over and you do it again, because there might be a little bit of an angle between these two plates, and we want to get rid of that. And there we go. Next up, and that's your result. Now you're going to need two holes here and here. Now, unlike the central hole, these do not have to be precise. So one thing you can do is you can just put this guy in the offset jig. So you can tell they just printed these, and use the same rig for this purpose. Again, these holes can be of any size you like. It doesn't really matter, just as long as you leave at least 2 millimeters here and 2 millimeters here. Now, for my own setup, I make these by the dozen, so I found it better to use a drill press. Nothing fancy about this one either. So, by the way, of course you can use a drill press for the center hole. Hit this too. Just don't make me redo it, because you should get the idea. Let me take a quick break and I will set up the drill press. In this case, instead of using a 3D printed jig, we're just going to use the regular vise. Now, this one can be moved, but that's strictly speaking not necessary, really. So one thing's for sure, I'm going to have to clean this up later. You know, general precautions with drills and drill presses. Use goggles. Measure twice, cut once. You get the idea. Now, the reason why this guy is off center is just that way I can get the right distance by simply making sure that it's flush with the end of the vise. Because I'm a bit lazy like that. There we go. Now the last bit of drilling you have to do is in the back of the slug for the laser. Now you want to use copper or brass slugs. You don't want to use aluminum slugs because their thermal mass is insufficient. This will of course go here. But we have to make a hole right here in the middle. Now for this purpose I made myself another little jig that goes with this drill press. You can use a regular drill with the setup that I showed you for this. You can actually use this jig into the white jig so as to help you center it. So you're gonna have to jimmy it in a bit, but you get the idea. And what you want to do is you want to make sure that the hole in there is conical instead of rectangular if you were to look at a cross section. So, why? Because it's healthier for the diode when you put it in there. Essentially, that's really the main reason why we're doing this. is go down, I don't know, maybe 1/3 of an inch, I would say. I'll do something fun. This is brass swarf. Try to microwave it if you don't care about your microwave. And this is what it should look like. And this is done because this way the pins on the laser diode can bend together and not, try to bite into the insulation as soon as they can. Okay, now that we have the Metalwork, all we have to do is we have to actually stick the diode in here, which we're going to do at the other desk. Alright, now the scary part. We have to get our diodes. This is a Nikia 660. This is an NUBM 660. The Nikia 7A75 has the same form factor. It's a little less powerful, but it has the exact same form factor and works the exact same way. There is a jumper on the board to select between the two diodes. And here it is. So we have the pin on the left is minus and the pin on the right is plus. So the first thing we're going to need is that we're going to need a length of this wire. This is going to be as keep this guy short. This is high current. This is silicone insulation. Because we want to make sure it doesn't melt. So let's say that a bit more than 2 inches. I would say 6 centimeters is adequate. It's probably too much, if anything. There we go, black and red. Oh, by the way, see this? The missing part here, this was actually cut by the laser. I was showing it off to a couple of young gentlemen that showed up here in a suit and tie, wanted to talk to me about God. And here's a trick. So there isn't a lot of room in here. There just isn't. So what we're going to do is we're going to forego soldering this, because in fact the last thing we want is, because this might get, it shouldn't, but it might get hot enough to melt solder, and the last thing we want is to cause a short. So we're just going to do this mechanically. We're going to insert these in here. The best way to do it, take a Dremel and give them a little bit of an edge. Just a bit. Just a little bit. There we go. Okay. This part done. All we have to do is, this is a diode, so if you get the colors wrong and you solder it in, the worst thing it will do is not run. You can just flip the wires. I'll try not to, please, because it makes the whole thing slightly harder to debug. And you just threading a needle here. Use whichever side of the wire you cut you prefer. Now, ordinarily this goes in faster with more light, but if I turn the floodlight, the camera doesn't pick anything up. So give me a moment here. Now be even. You gotta make sure that you hit the center of the wire. Very important. There should be no bulges on the silicone, because otherwise that's probably where the silicone will break if this thing vibrates. There we go. That's one. Now this guy is going to be mounted pretty solidly in there, so there should be no vibration issues. If there are, I haven't detected any in about 3 years. There we go. don't go all the way down. Don't go all the way down because you don't want strands to touch each other or touch the body of the diode. Push these together a little bit, together, and a little bit in the middle, like so. And then again, you gotta thread a needle. Seems to be a bit of a thing with this build, eh? Now this guy should just fit if you've done the hole right. If it doesn't, you just leave it outside of it like so. You take another one of these and you use it to gently push the diode where it's supposed to be, like so, and then you open it back up. So that's your result. Now, one thing you can do and one thing you should do is add a bit of thermal paste. Strictly speaking, that is optional, but I prefer to do so anyway. You will need, something like a screwdriver to put it in there. There we go. You can also, of course, put the thermal paste in before you put this guy in. And if you can do that, you probably should, but you don't have to. Above all, make sure you don't mess with with a little bit of glass that covers the diode proper. Any crap there will reflect back into the diode and mess it up fairly severely. In doubt, if you absolutely have to touch it, if you have to clean it, you use a piece of the kind of cloth that you get to clean eyeglasses with. Okay, so all we have to do now is put this guy in there, and that is our diode assembly. Now, this is the part where you want to put a bit of force here. You want to get something. You want to clamp this, and you want to screw it in with more force than your mortal fingers can give you. Now, I overdo it slightly, and I use this. Now, that's just me being me. Now, the good thing is that none of this is touching the diode. It's just brass touching brass. And there we go. So this is our optical assembly. Of course, now we're gonna have to put in the lens and the little spring to hold the lens in place. Now, I find when operating these things that the optimal focal length is 3 to 4 inches, 7.5 to 10 centimeters. So that means that your lens will be almost all the way out. However, for shipping, I tend to ship them with the lens all the way in because, one, there's less crap protruding, and two, that way the laser is out of focus, so if somebody does anything stupid, they're somewhat less likely to lose an eye. What I tell people is that you should treat this as if it was the barrel of a gun. If it can see you, it can burn your eye off. There we go, put a little crown on it. This is definitely optional. One thing you can do is you can kind of hold this. Go this way. There we go, that's better. Alright, all we have to do now is get the two parts together and put it in a shroud, which we'll do after the break. Alright, time for final assembly, hopefully. What we got here is all the parts Now, one thing we're going to have to do is we're going to have to short the PWM to the plus V for a moment, because that's just one less thing to hold up. So the best way to do this is connect it to the out plus on the 4005. There we go. Very briefly so that it can be taken off later. And this is where this guy goes in here. You see the holes? So you put it in there. Don't solder these yet. We're going to do a power test before we do that, because it's a pain in the ass to desolder these. So here it is. Again, we're going to go red, black, black, red for these. That's how they're connected. Alright, there we go. Nothing unusual here, you just, soldering. So these wires are a bit too long, but it's not a big deal. The LM338s are in constant current mode, so they're not going to do anything too stupid. You want to make sure that you don't have these things do not fray, because otherwise they will short the diode. It will not kill the diode, the laser will just sit there and not laser anything. You may pay to tin these guys before you do this, actually. There we go. For what it's worth, this takes less time if you're not trying to show it to a camera. Okay, so this is what it should look like. Now we gotta power it. I have a ATX power supply for this. To see if it works, all we have to do is that we just give it power. The fan should turn on regardless of orientation, and the laser should only turn on if this guy is vertical. Before you proceed, safety first, or at least in the top 5, please. Goggles. Safety goggles, very important. For this particular laser, this is 455 nanometers, so beige will do and green will do. I sell them with green lasers because I find them to be the safest. I generally test them with the beige lasers because they let me see more of what's going on as I work. So first test is going to be, aim it someplace sane and give it some juice. The laser will not turn on, however, the light is on the 4005 will turn on if there is one, and the fan will turn on. And that's all we want right now. So this is the part where I'm going to cheat a little bit. I'm going to see if I've done anything stupid, but I don't think so, but I'm going to make a break here anyway. So what we want to see here is that, again, if I give it power, the fan should turn on, but the laser should not. Let's see if that's true or not. I said I was going to cheat, but I decided not to because I want to show you something interesting. As you see, the board works and the laser turns on. Why? What did they do that's so wrong? Simple. You can see here that I have put a second 47K resistor for the LED on the tilt switch, where of course it wants a 390 ohm. Not a fatal mistake, however, that means that our security system is not operational. So what I'm going to have to do now, and I'm going to do it off camera because it doesn't show you anything new, is I'm going to have to desolder these two wires, open the hood so to speak, and replace that resistor. See you in a bit. Alright, so I have replaced the resistor that allows the LED to turn on properly. So we can close the hood, resolder these two connectors. To me, it's important that this kind of design be easy to fix and easy to modify. That's why there's a prototyping area on it. So let's get rid of the legs for the new resistor. And let's see if it works properly. Again, I'm gonna short the Pwm input to plus V, just so that I have to hold fewer things with my hands. When you test this guy, be sure that you know where you're shooting at. Don't want it to be reflected on you. Now, this is not vertical, obviously, so what we should see now is the laser not turning on, but the fan turning on. And this is in fact what we see. Note that the fan is kind of trying to take off. These are good fans. Now this is out of the way. Let's keep it on. And just for a moment, let's turn this guy vertical and see if the laser turns on properly. Well, you know it does. There we go. Okay. Now that we've done all of this, what was the reason for it? The reason for it is that we haven't soldered these in yet. And we want to because, again, thermal conductivity is important in the design. By the way, while I'm here, one note. The reason why the heatsink is shaped like this, when I first offered the design to people, they were like, you know, your heatsink is backwards, it should be mounted 90 degrees, it should be mounted 90 degrees. The reason is that I actually want turbulent airflow here and here, because we got some air goes down, hits the workpiece, and, you know, gets rid of the fumes. Some air vortexes here and here that actually removes heat slightly more efficiently, we found. In addition, it's, you know, easier to put together. That's always nice. So the last thing we gotta do, we gotta solder this guy. Now note that we have used a NUBM 660 for this, so you can get the full 8 watt of power. So the last thing we're gonna have to do before we put this in the shroud is close the jumper. That will bypass some of the resistor traces. The jumper's right here. It's right here. See these two little holes? Basically you want to plug them. Obviously, if you're working with a 7875, you don't want to do that because you'll blow out the diode. And there we go. This is a completed L-Cheapo effectively. Now we got two options. We can either put this in a plastic shroud or in a mixed material shroud. This is the plastic. This is what I generally sell. On request, you can also put it into a piece of 2x2x3 aluminum. I just buy these. In which case, the shroud is somewhat different. It goes in like this. I personally recommend using the plastic shroud if you're upgrading a 3D printer because it's lighter, and the aluminum if you are building a standalone tool, because it looks slightly better and because you don't care about the extra weight and because the aluminum does touch here, so it helps with the heat dissipation. For now, let me show you how it's done on the plastic part. So this is a tight fit. It's intended to be. So you put it in like so. Let's make sure to not pinch the fan. Push down. Of course, make sure that the flanges touch the plastic support, and then push with your fingers like this. You're fairly likely to leave a mark here and here, but we don't care. This stuff is pretty flexible. It's supposed to be. The idea here being, of course, that this makes it easy to, move around. There we go. Decent fit. So now we're gonna need a couple of zip ties. This wire here you can put in, you can make it stay in or you can leave it out. I prefer to leave it out, that's just my personal preference. And the zip ties go in like so. The fan holds the remaining piece in place against the plastic. So don't forget, you gotta disconnect this too. Now you can use screws for this job, but again, I prefer the lightness if this is good to go on top of a 3D printer. It should be as light as possible because the carriage is already handling the extruder, and this guy weighs about 100 grams. So when it's moving quickly because it's back in printer mode or it's engraving, you don't want to put stress on the caddy if you can help it. Just reel it in. Very nice, very simple, very easy. And here's your completed L-Cheapo Mk5 laser. The Mark IV is built exactly the same way, except that you don't have to do this part. You can just use a regular 4005. You set it at the same voltage, and you do not put in that jumper. So this is what the back of a Mark IV is going to look like, and this is what the Mark V looks like. This is the end of the video. It took about an hour to build this thing. It takes less if you are not on camera, obviously. and you know, buy one from me, build it yourself, but beware of imitations. L-Cheapo is made in the US, right here, right just as you saw it. This is the end of this presentation. I hope you enjoyed it. Do look up the wiki for parts lists and for schematics and for where to download the Gerber files for this board. If you want to do it the old-fashioned way, you can also just get the schematic and solder in a bunch of 5.6 ohm resistors, which I still have some left over. So that's the end of that. An addendum to the video. So I want to show how to also use the aluminum shroud. So this is a 2 by 2 by 3 inch 3mm aluminum. This is the variant mount for one. You just slide it in like you do with a plastic one. Nothing crazy about that. And you don't need this part because this is being held up by the tilt switch. So on this one you pass the fan wire here, and note that in this case you probably want to bend these guys a bit. Because in this configuration the fan goes on top. So what are we gonna do here? We're gonna take the aluminum part, note where the cutting curve is. This should fit, just press fit it. Make sure that it touches, because we might as well use this thing for further heat dissipation. Nice and flush. There we go. And then in this case, the fan goes on top. There are two little channels for the zip tie to go in. And again, the last step should be to get the zip ties in and tighten them. Now you want to tighten these very much, as they will let you, but you don't want to do one and then the other. You want to do both roughly at the same time. And then, you know, you can cut them or do whatever it is that you want. So this is what it should look like when it's done. As you see, the more you tighten these, here you can kind of, you know, guitar it a little bit. There we go. There we go. There it is. The end result is pretty tough. You can, you know, the user can make their own holes in these if they want. That's the result out here. One thing is that before we ship these things, we generally run them for half an hour to 2 hours to make sure that the diodes are burned in and that the user will not experience it dying after a few minutes. It's not common, but it happens. So that is the variant aluminum shroud. Note that, again, I don't recommend doing this if you have a 3D printer because it just made it heavier for no real reason. But it might be good if you are building a dedicated tool. You know, let's say that you got like a Chinese laser engraver. You can chuck that laser, you can put this one in, and you're good to go. On that note, if you do, remember, this guy takes 12 to 24 volts, so it will run on the 19 volts provided by a laptop power brick. You can get those for cheap. Any laptop made this millennium will work, really. So here's the real end of the video. This has been Spirit Plumber for Robots Everywhere. Build these things yourself. You can find the parts list on my website. Buy it from me if you don't want to build it yourself. But whatever you do, beware of imitators. The L-Cheapo is only made in the US, and now you've actually seen where it's made and how it's made. This is the strongest solid-state laser currently available. It will work for a long time. It has no peak output because that's the whole point of the self-thermoregulating design. So your output is going to be roughly 8 watt. I try to guarantee a bit more than that. And that's it. That's all I got.